Hello, welcome. This is my final project for my cognitive science class. Here is, this project is a research proposal. This is based on an idea called cognitive atomization, which is described as splitting associations at the cellular level using NMDA receptor antagonists. So we will briefly go over the concept. Then we will talk about long-term potentiation, summation, classical conditioning, NMDA receptor antagonists, and the effect that they have on these processes, optical illusions, and visual agnosia, and lastly, dementia. And then from that point, we will go into the methods section to talk about the proposed experiment. So the general concept is based on NMDA receptors that are very ubiquitous in the brain. They are quite common on most of the neurons. I think I've heard it's about 50% of the neurons, but that might be wrong. I don't know. But it is very common. I know that. So these receptors are thought to be a cellular mechanism in learning, in coincidence detection, and something called summation that we'll get into in a little bit. They are involved in classical conditioning, which is basically like reward and aversion conditioning. And so the basic hypothesis here that we are exploring is that blocking NMDA receptors might produce a reversal of previously learned associations. And this kind of goes against what some of the research says now, which basically says that NMDA receptors are involved in encoding, but not involved in retrieving memories. So they basically say that when you block these receptors, you cannot learn new information, but you can recall previously learned information. But there are a couple reasons why I don't think this is entirely true. And I think that it's because of dose dependency. I think that a lot of these studies are probably using very small doses, especially the ones in humans. And because some of what humans report when they recreationally use these compounds, they often report losing access to their long-term memories. And so we'll go over that in a little bit. We also explore optical illusions, which I think are based on this mechanism as well. I think that you can view the illusions as a kind of learned phenomena. And there will be a whole section on that as well. Okay, so so I should mention as well that this has implications for schizophrenia because individuals with schizophrenia they have less function of this receptor. So they have less activity at NMDA receptors. And that is reflected by also the way that they often have problems with associative learning. In the animal models, they do not have long-term potentiation. There's problems with summation, and there's changes in the way that classical conditioning occurs in individuals with schizophrenia. For example, they often have an impairment to reward learning, but or reward processing, but not aversion or punishment processing. Okay, so we'll start with long-term potentiation. There are two major glutamate receptors that exist on a huge amount of neurons in the brain, and that would be the AMPA receptor and the NMDA receptor. So there are some interesting differences between these two receptors that might help to explain why some of the effects occur, different effects occur depending on whether the neuron is bound at the AMPA or the NMDA receptor. The AMPA receptors are often first to be stimulated because the NMDA receptors are blocked by magnesium ions. And this makes it so that, okay, so I should also mention they are glutamate receptors. I think I might have already said that, but basically glutamate binds to either of these receptors and activates the neuron and stimulates it. And NMDA is blocked from this because it has magnesium in the way. And when the AMPA receptor is stimulated by glutamate, this opens up both the AMPA receptor channel and the NMDA receptors, so that means the magnesium can actually leave the NMDA receptor. So that means that over time, the more that AMPA receptors are stimulated, that means the magnesium can be unblocked. It could unblock the receptor for NMDA and allow glutamate to bind at that receptor. And this has different effects. Mostly, this different effect, one of the key differences is that AMPA receptors are very short, like 1 millisecond time periods or even less. And they often fire really fast, and the effects on the neuron decays really fast. So it's just on off. And with the NMDA receptor, though, it can last much longer, magnitudes longer. Like, I think it was something like 100 milliseconds, or I think even 500 milliseconds, but I would need to go check again on that. But it is at least 10 times longer to decay compared to the AMPA receptor. And this is important because if we think about associative learning involving coincident occurrences of stimulation on neurons, like two neurons firing at the same time and then being associated to each other because they were coincidental. If you think about this longer duration, that means that there's a lot more time that that those if two neurons are both activating their NMDA receptors, that means that the neuron will stay excited for a longer period of time and give a larger window for simultaneousness to occur. So if it's only the AMPA receptors that are firing, that means that the neurons will decay really fast, and the the two neurons firing will likely not overlap. There'll be one will be on, the other will be off, and by the time the other one turns on, it'll already be too late for coincidence. So, in essence, the longer duration of activity on the neuron gives a larger window for two neurons to be turned on at the same time. And so this has led, there's been research about the involvement of NMDA receptors in like Hebbian learning, which is basically the idea of like neurons that fire together, wire together. It's been studied in long-term memory, associative memory, and as a coincidence detector mechanism. And schizophrenia, since it has this impairment in NMDA receptor activity, long-term potentiation, and also associative learning, um, this means that like that this might help explain some of the effects that happen to people who have this condition. And the hypothesis I have is that basically um, that if you block, well, there's a couple, I would say. If you block these receptors using drugs, that it will prevent people from being aware of coincidences, and that optical illusions may kind of reflect some part of this. I think the optical illusions, well, we'll get into that. I think for now, let's just move to the next slide. Okay, so another important element here is this idea called summation, which is coming from the word sum, which is like adding together. And so summation refers to a process where either temporally close stimuli, as in firing really close uh, in between, like with a smaller gap of time, produces an increased reaction on the neuron. So you can imagine that how I mentioned earlier, this idea that neurons have a decay in their uh, stimulation, that they kind of slowly phase out and become silent again. Um, you can imagine that if the neuron gets stimulated again before that decay happens, that you get an increased response from the neuron. It adds both the new stimuli and the old stimuli that's still fading out together. And uh, so the idea of temporal summation is basically that. And then if we think of spatial summation, you could imagine that two neurons uh, both feed their stimulating signal to the same third neuron, so that if both of those two neurons are sending their stimulation out at the same time, that third neuron receiving the signal has an increased response that is the combination of both of those two neurons. And this may play a role in associative learning. Um, some amount of perception and cognition may rely on kind of layers of this summated activity. I sort of have a hypothesis that summation is like a huge part of a lot of our conscious experiences. I think that like the higher you go in processing um, in the brain, that the more summation is going to be involved at that point. Um, and then there is this interesting test in schizophrenia known as pre-pulse inhibition, which I think may be related to summation. There is at least one study that talks about this connection, that the startle responses in this test may represent or measure temporal summation. And basically, this pre-pulse inhibition test is that they send two noises to the subject. The first noise is quieter, while the second noise is very loud. And the normal subjects will, if you give them this pre-pulse that is quieter, they will not get a startle reaction as intensely from the second louder noise. So with the schizophrenic subjects, though, they experience the startle response regardless of the pre-pulse. They respond as if there was no pre-pulse, and so the pre-pulse may have a summation effect perhaps on inhibitory responses in the case of the normal subject, but in the case of the schizophrenic subject, the events may not summate. So this might be because there is no NMDA receptor activity going on, so that um, so that how I mentioned with the AMPA receptor, the neurons decay too quickly. Like the prepulse may have an effect that would uh, buffer the response to the startling uh, signal or the startling noise, but with sorry, I need to turn the phone off. Anyways, um, okay, so with the prepulse inhibition, it may stimulate some kind of inhibitory response, but maybe it decays very quickly because it is only on the AMPA receptor. And maybe if we did the prepulse inhibition where the startling sound was a few milliseconds or something, then maybe they would respond similar to normal, but probably I feel like even in that case, it probably doesn't work like that. But you can kind of see this connection with temporal summation, how prepulse inhibition might kind of represent a similar tendency. It might be a problem of summation. And this theme will come back in a little bit. Okay, so here is a diagram. It's kind of not very exciting, but this is an example of two different neurons right here. This is one, and then this third neuron is being stimulated by both of them, and it has a summated response. Next, we have classical conditioning, which is something that's usually talked about in terms of dopamine and sometimes also endogenous opioid chemicals. Both of these are thought to play a major role in reward and aversion conditioning. And there was one study that noticed dopamine coactivation with the NMDA receptor is critical to appetitive learning, which is basically just classical conditioning. They found that specifically there's a dopamine type 1 receptor, and both of those need to be activated at the same time for this kind of learning to occur. And there's this one of the opioid receptors is the mu opioid receptor. This is thought to be rewarding, and it happens to stimulate dopamine activity and glutamate activity, both of which will support this coactivation process. So you could imagine that the role is that if some kind of behavior is rewarding, these opioid chemicals will release and stimulate the mu opioid receptor and enhance the coactivation of dopamine with the NMDA receptor. And then on the other hand, there is kappa opioid receptors, which are aversive instead. They are not rewarding, but instead they are dysphoric. Studies have shown that like stress related aversion has been able to they found that it was mediated by the kappa opioid receptors. And there's other research showing that if you block these receptors, that you get stress resilience. The study showing involvement of the kappa opioid receptor in aversion also involved a second uh, neurotransmitter called CRF, but we won't really go into that too much. So the interesting thing about this, so the brain's kappa opioid receptor binder is called dynorphin. that is what I will refer to as refer to it as from here on out. So this dynorphin suppresses dopamine release and can directly block NMDA receptors, which antagonizes both sides of this coactivation process, preventing uh, reward learning. And what is interesting is that schizophrenics show elevated dynorphin and kappa opioid receptor agonism, which might tie into how they seem to have intact punishment learning, but not reward learning. And the lack of reward learning seems to match with other data showing that there's reduced mu opioid receptor densities in the brains of schizophrenics. Okay, so now NMDA receptor antagonism. This is mostly drugs like PCP, ketamine, and dextromethorphan or DXM. These drugs seem to produce psychosis. They're used as animal models for studying schizophrenia and psychosis because NMDA receptor impairment has been seen in schizophrenic subjects. And these drugs produce amnesia. They are also used as anesthesia. That is their primary use in humans, basically, that with the higher doses that people seem to become unconscious. But I think that one could kind of debate what is going on there. Like, you could also argue that people are not becoming exactly unconscious, but they are having like a loop of amnesia that they can't respond to anything because they keep forgetting it before one can actually form a reaction. And so studies on these chemicals, these NMDA receptor blockers, they show that there is a learning impairment, that they cannot encode new information. It blocks associative learning and does not block long-term memory access. And the experiment here that we are going to propose directly contradicts this. It says instead that this may be dose dependent because some of the effects that people get, according to the source, the Psychonaut Wiki, which is not necessarily the best source. It is a wiki made by just kind of probably not scientists, although I'm sure some of them might be. And it is based on anecdotes, but the descriptions are very vivid and well written. And I think that it is worth looking into based on what a lot of people seem to be reporting, which, as an example, there is a page on the Psychonaut Wiki that talks about memory suppression, and the way it describes it is dose dependently. So for example, in the lowest doses, it says that short-term memory begins to fade, and then in higher doses, it starts to entirely cut off short-term memory. And then as you increase more, then long-term memory access starts to be blocked and you start to forget common or basic things about your life, like where you live, who you are, or that you are even human. And then in increasing doses, people may just be kind of disconnected entirely. And this, I think that a lot of the studies that have been done on these drugs have maybe only studied low doses. And I think that the reason that researchers might want to go this route of studying low doses is because they might assume that these kind of other crazy effects that happen under the effects of the drug, like say anesthesia or the loss of consciousness, that these kind of things might be a confounding variable or something like that. Although I haven't seen mention of this, I just think that maybe a lot of researchers might think that I think it makes sense to think of it that way personally, that if there's like these hallucinogenic effects, which are commonly reported, that these might be complicating observations of just impairment of memory access or something like that. That maybe, like for example, if the animal or human is in some kind of stupor state, that they would obviously fail the long-term memory task because they might be completely unresponsive. And I think, though, that some of these things are arguably the direct effects of blocking uh, conditioned brain processes, basically blocking long term memory. I think that one could argue that these really established memories are less sensitive to the effects of these drugs compared to uh, brand new memories. Like, for example, if you're just learning something under the effect of the drug, this is a completely non-reinforced memory, and so this might be the easiest connection to just abolish quickly. So here we're basically hoping to study whether this whole process is dose dependent. And let's go to the next slide. Okay, so it's worth mentioning, I think I've already stated it, but they can block long-term potentiation, summation, and here it says reverse long-term potentiation. This needs to be corrected, actually. That's not necessarily true. There was one study that noted that it can actually preserve uh, already potentiated systems, and uh, we won't even go too deeply on that, but uh, these drugs impair pre-pulse inhibition and induce hallucinations. These drugs are currently used as models for schizophrenia. They induce amnesia. Okay, so most of this is what I've already stated. So, so the study in humans used ketamine, and it used a dose that was considered a threshold dose according to the Psychonaut wiki. And the results of the study do fit with what's described on the wiki. And so I think this is important because like pretty much all the research is reporting these results, and there's very little mentions of uh, higher doses, especially there is none in humans. And it makes sense too because of the ethical problems behind studying this, studying the higher doses of the drug. Okay, so this is another important element here. There are paradoxical effects associated with NMDA receptor antagonists in the research. There has been cases of enhanced memory after strokes, and I think the stroke might present a special condition, but I also think that um, part of this might be that it's protecting against, well, this gets like really complicated. I forgot to mention this earlier, but that dynorphin um, neurotransmitter that is related to kappa opioid receptors and blocks NMDA receptors. Something important about that is that its release under situations like seizure and protects against excitotoxicity, which is mediated by overstimulation of the NMDA receptors. And so this is kind of important. It's like, so dynorphin is found to release under the condition of seizures, um, and it seems to act as the body's anticonvulsant. It stops the seizures, and um, so the thing is, like, there's been research on NMDA receptor antagonists for neuroprotection, but they've also found studies like showing increased brain damage and neurotoxic effects. And so like in the case of stroke, it might protect against neurotoxic effects and also even prevent an increase of dynorphin that might normally release to try to curb the damage involved in these stroke incidents, because the one of the main ways that dynorphin releases is by stimulation of the NMDA receptor, and then it can block the receptor, presumably as a way to prevent brain damage in case of emergency situations like seizure or stroke. And there's research showing dynorphin is linked to like cognitive decline in aging rats, where if you remove it, if you remove the dynorphin genes, there is no cognitive decline. There's also links of dynorphin to Alzheimer's, schizophrenia, like a lot of research showing different forms of cognitive impairment associating to dynorphin activity. And it makes sense because it's blocking learning mechanisms, reducing dopamine, which is involved in learning. And so when you use ketamine, it might be stopping that. And there is studies showing now in 2020, there was one showing that the prolonged beneficial antidepressant effects of ketamine require desensitization of the kappa opioid receptor, and it requires that that receptor be bound by ketamine during the effect of the drug. If you block ketamine, if you block the kappa opioid receptor while using ketamine, the antidepressant effect doesn't happen. And this also makes sense because there's research linking dynorphin to depression, like I mentioned before, dysphoria, and all that. Okay, so the other part here is that there are paradoxical effects with uh, these dissociative anesthetic drugs, NMDA receptor antagonists. They can uh, seemingly increase glutamate activity, even though they block glutamate receptors. And part of this is probably because some of the glutamate receptors that are targeted earliest are involved in enhancing GABA activity, which is an inhibitory mechanism. So normally, the glutamate activity in at the GABA interneurons may help with reducing glutamate activity, and so the NMDA receptor antagonists are blocking the inhibition there, allowing for an increase in activity elsewhere. And this might actually enhance NMDA receptor activity depending on the dose. So, for example, like even though seizure disorders are linked to high activity at the NMDA receptor, um, they have also found that you can get seizures with very, very low NMDA receptor activity, which might be because of some of these problems occurring here. And another important thing that I already mentioned is that ketamine targets kappa opioid receptors, and so for example, like some studies show that ketamine enhanced fear memory, but dynorphin is like critical to fear memory and learning. And that might be different from other kinds of learning in some ways. Like, for example, how dynorphin seems to block some of the classic learning mechanisms and block reward learning. So that the kind of learning that's enhanced by ketamine might be due to basically acting like dynorphin. It might be a specific case that doesn't apply to all NMDA receptor antagonists. We don't yet have evidence to generalize this, as far as I know. Okay, so that was very technical. Now, this might get a little bit more interesting and a little bit less biological and overwhelming. So, illusions. So, individuals with schizophrenia often have immunity to several common illusions. This includes the Chubb illusion, which is this contrast based illusion. There's the Ebbinghaus illusion, which has to do with size. I have a picture I'll show you in a minute. The three flash illusion, which I also have a video that I will show you in a minute. And the Muller-Lyer illusion, and also the inverted mask illusion. And I have a couple demonstrations to show you some of these. Illusions here, I argue that they are a kind of perceptual autocorrect or predictive perception. So basically, well, I'll show you examples and you'll start to kind of get what I mean. I'll explain while I show you the examples. So, NMDA receptor's role in learning and summation may extend to the visual system. Okay, whoops. So, this is not supposed to be here yet. This comes later. Wait. Okay, so just give me a second while I find out if... Okay, so somehow my slides are mixed up. I didn't realize this. Sorry for that. So the illusion test is, let's see. Okay, let's just, wow, I think this didn't go to the order that I thought. Okay, so well, here's an example of the Ebbinghaus illusion. And you see that this and this circle look like they're different sizes, and that is not true. This illusion doesn't work as often in people with schizophrenia, and that is also true of, I think it was the Muller-Lyer illusion. Doesn't work. They tested the Muller-Lyer illusion in monkeys and found that when you use NMDA receptor antagonists, they are less sensitive to this illusion, similarly to people with schizophrenia. And so basically, the argument here about learning is that we are we have such a frequent encounter with comparing, like, say this illusion, we can compare sizes based on their surroundings and form conclusions about their actual size based on this. Like, for example, this here is surrounded by large objects, so it seems small. This is surrounded by small objects, so it seems large. It is a generalization. And so let's look at this one. This one is tested in schizophrenics, and they do not respond to this illusion as well. Like, look right here. This, when the mask is turning, you observe that it looks like the mask is facing towards you, even though it's facing the opposite direction. And this is, I basically argue that this is because we are so frequently exposed to forward-facing faces, and we never see inverted masks. That that this is a very unlikely situation. Sorry, I'm kind of getting distracted. Okay, so I'm going to see. Okay, there. Um, Everything is lagging like crazy. I'm noticing, but okay, so basically, I think that what kind of happens with an illusion like this is that you um, your brain predicts what you form expectations of what to see, and the more that your expectations are validated, the more that you see that you correctly predict a forward-facing face, the more that you don't have to look at the uh, the environment as much or pay attention to the details of the environment, so that your brain just assumes and kind of autocorrects what you think you should be saying based on the data that you've had in the past. Okay, and let's see. There's probably, I think there's one more. Here's the 3 flash illusion. If it loads, here we go. So this requires sound. I'm going to make sure that, yes, computer sound is sharing. Okay, so basically what happens there is um, if it worked for you, then that probably looked like you saw like 3 or more flashes. I showed this to a couple people, and they usually report 3 or 4 or more sometimes, but usually 3 or 4. And it's actually only 2. But the thing is, you can distinctly hear the sound, and the sound is 3 beeps. And when it's paired with the 2 flashes, um, you kind of associate those 2 occurrences as coincident. You kind of are your brain is kind of assuming that the flashes and the sound are connected. That maybe the flash is creating the sound or causing the sound, is a kind of like causal assumption. And this is another illusion that those with schizophrenia do not experience as often. And this is also kind of like a autocorrect. It's the flashes are pretty hard to see because they occur in such a short time span, but you can pretty distinctly hear the 3 sounds. And so your brain kind of assumes that you maybe missed one. And I feel like the value of that, like if we think of evolutionary purpose of something like that, would be that you blinked and missed one of the sound or one of the visual things, for example. And when schizophrenics are lacking this, I basically am arguing here that the blockade of NMDA receptors is preventing temporal summation and coincidence detection. Okay, so there is also the well, I'm gonna come back to this. We have to go back to okay, we have to go back. Sorry, everything got out of order without me realizing. Okay, so now we can move on to this agnosia. And this gets kind of interesting because so what visual agnosia is a failure of object recognition, and this can be either aperceptive agnosia or associative agnosia. And aperceptive agnosia usually is a more sensory problem that um, like probably objects do not even look familiar or look um, uh, okay, it's better to explain, I think, what the data shows. So, like with people with aperceptive agnosia, they can't even draw pictures to recreate the thing that they're looking at. Whereas people with associative agnosia, they can't tell you what they're looking at, but they can still perfectly replicate what they're looking at. So it implies that they still see things kind of like the way that most people do, except they are maybe having a disconnect with naming that uh, object or perception. And this gets interesting because the Psychonaut wiki about NMDA receptor antagonists talks about this effect of suppressing pattern recognition. And they note that this is similar to visual agnosia. And so if you look here on the left, this image, this is one I've liked in the past. It is a recent meme that was spreading on the internet titled Name One Object in this image. And you could probably tell by now if you look closely, all of these things look somehow familiar, but they are kind of incomprehensible. There's like nothing identifiable here. And so that might be a good model of agnosia, although we can't necessarily be sure, you know? It's very hard to study these kind of perception things. And here's kind of what I was discussing a minute ago. So with associative agnosia, you can see that the participants replicate the drawings pretty much identically. But here, this is where it gets weird. Aperceptive agnosia, they do not really replicate the objects much at all. But what's very fascinating about this is that there are clear patterns here. And I've color coded this to kind of identify where things overlap. So if you look at the X, we can see it's two lines separated. And this is the X shape is two lines. And then if we look at 4 here, it is these two lines again. And you can see that this is really actually an X shape as well, but it has this curve here, right? The 4 has a curve. And here you can see, if you see my mouse, I'm not sure, but at the very bottom of the agnosic representation, it is curved kind of like the 4, and it is following the same pattern as the X. And if we look at circles, seems to be spirals here, and then here also spirals, and this is also a circle shape. And here the O is having some kind of spiral as well. And then if we go to A has two lines and a circle representation in the agnostic perspective, it seems. And that kind of fits because it kind of has a similar shape as the 4 and the X, but not exactly. And then here with the 3 and the B, the normal perspective, you can see that a B contains the shape of 3 in it. Right here, right? It just is a 3 with a line. And the agnostic representation has this strange curve here, like say the 3. And that shape is also here in the B agnostic representation. But this has two lines going along with it. And that's pretty much, we could stop there with that, but it's pretty fascinating to consider that there are still consistencies that seem to even correlate with consistencies in normal perception. I think it is very strange, and I wish I knew what their experience is like. Okay, so we can get on to the methods section now. Okay, so there will be 6 tests. each test will have a before and after the drug condition, and there will be a placebo group as well. Um, so the before and after I'll explain for each test. And each test will be shuffled and performed randomly rather than, like, say, there's like a series of illusions. We can mix that up with the other tests, like the video memory test and reward conditioning tests and stuff like that. Okay, so the drug that will be administered is going to be dextromethorphan. This is better than using ketamine for a couple reasons. Dextromethorphan is widely available and legal. It is over the counter, for example, and it is also, I don't think it is a kappa opioid receptor agonist like ketamine, so that might remove that kind of confounding variable where ketamine might enhance certain kinds of learning by a different mechanism that has nothing to do with the NMDA receptor, for example. Then, okay, so there'll be 4 groups. There'll be a placebo control group, a low dose group with 2 milligrams per kilogram, a medium dose group, 5 milligrams per kilogram, a high dose group at 10 milligrams per kilogram. And these doses are chosen to reflect William White's DXM AFAQ, or FAQ, which, if you, most of you may have not heard of this. This is a fascinating document that someone just completely collected like a lot of information about this DXM drug and compiled it into this massive document detailing effects of all the different ranges of doses, talking about how there's distinct changes of effects that aren't just that it isn't just a spectrum. There seems to be like a kind of like switches that get flipped at each dose range where the effects drastically differ. Like, as an example, people report stimulation and euphoria and even empathy at the low doses, but then at the high doses, people feel numb and unemotional and unempathetic. And so it's kind of interesting that the effects can be opposite. And this kind of gets back into this whole problem of the paradoxical effects and how you might even see increased glutamate activity with a glutamate blocking drug. And so that's kind of the aim here, is to all of these doses are taken from the document to reflect what William White described as plateaus, which are these distinct layers of effects. So we are going to omit the 4th plateau only because we believe the high doses are risky, and we'd rather just not risk too much. I suspect that we'll see differences in these dose ranges already, and it's not necessary to take that risk. And so we'll have a medical response team prepared in case of any problematic effects. A low dose of lorazepam will be handy if the participant wishes to abort the experiment. This might be especially useful because, it was mentioned earlier that NMDA receptor antagonists, part of their effect is that they reduce GABA activity, and this can make some of the participants very anxious, and this would directly counteract that. And if you look at something like alcohol kind of is an effect of NMDA modulation and GABA enhancement. So it doesn't have like the typical dissociative effects, maybe partly due to the fact that GABA is involved in the effects of alcohol. So the person might go from tripping out and freaking out to come down and be in a better state of mind. Okay, so the subjects will be chosen from universities. They will be at least 24 years old so that we avoid any kind of conflict of the developing brain. It will require that the participant has used some form of dissociative in the past, so that they've tried ketamine, tried DXM or PCP or whatever, just so that they are familiar somewhat so that they know what to expect, and there is less risk of people aborting the experiment if they already know what they are getting into. Okay, so the other interesting uh, part of the methodology here is that we are going to use Zoom in the experiments. And the way that we will use Zoom is that this will allow us to gain participants from multiple universities and expand the subject base by collaborating with other labs. It will also reduce, it can help to reduce problems with exposure to the coronavirus during the pandemic. It helps with social distancing. It will also potentially make the experiment cheaper, uh, and we can synchronize what the participants see and reduce problems with having multiple like people describing the tasks to them. It could be one person describing the task to all participants at the same time, so that there's no difference in the influence of the person giving the instructions, no separate biases. If there are any biases, it will just be one bias to all the participants, for example. And there will be an assigned local uh, temporary lab assistant who's had previous experience in doing human involved experiments. And so, like at each different university, someone will be there present to monitor and stay with the participants in case something goes wrong, and to just help record things and stuff like that. And okay, so I think that covers most of that. So the first test is reward conditioning. The reward conditioning task will involve pairing tasty snacks like Oreos and potato chips with a background soundtrack that has a somewhat unexciting impact on valence. So you could imagine maybe a neutral sounding song or something that isn't terribly euphoric, um, or yeah. So then we'll pair this with feeding Oreos or potato chips to the participants in recurring episodes with the music over the course of, say, 5 sessions or so. And we will make sure that uh, that their feelings towards the song has enhanced, or also that the craving of the food is triggered by the song. And only one Oreo or chip will be given at a time, with intervals in between so that it's paced, and that the participant is not just allowed to freely indulge, but instead is continually experiencing the craving for more of the snack, so that they're not satiating it entirely, and we're priming um, this craving response, associating the craving with the music, and associating that state of craving with the music. And the conditioning will take place many days prior to the drug condition. And once the drug condition comes, each different group will be given their drug. And after about, so with all the experiments, they will occur about an hour and a half into after the dose has taken hold. We will also check the subject to make sure that the effects are present. We might not expect much effects at the lower doses, but for the higher doses, they will probably be very noticeable. The person is probably going to be quite aware of the effects and will try to make sure that that is the case. And we will report if the participant notes no effects. Okay, and so during the drug condition, the song will be presented and the participant will be asked if they crave the food or if they how they feel about the song. Do they still have an enhanced reaction? So I should mention, uh, the day of the test, before the drug is given, it will also be tested. Their response will be tested again before the drug, to make sure that it's still there. And then after the drug is taking effect, then we'll ask them again to make sure that they to see what response the drug produces. Then we will do an aversion conditioning test. This will involve a shock sensation paired with a sound. The sound will occur uh, uh, very shortly before the shock is administered. So maybe like 20 milliseconds before the shock is administered, so that the sound of um, the sound that is paired with the shock will uh, create an anticipatory effect so that when they hear the shock, they will anticipate that they will be shocked soon after. And this will be repeated in multiple sessions over the course of, say, like 3 days, 3 sessions or so, until there is an automatic flinching response, uh, and that we will check their heart rate using an iPhone app that checks heart rate, and to see if there's any increase in response to the sound and to make sure that conditioning has taken hold. And okay, so, and I guess next would be the drug condition. We will separate the groups and uh, sorry, this is like going on so long and I'm kind of losing my train of thought for a second. Okay, so under the drug condition, the participants will be tested again at like 1.5 hours, and we'll see the if the sound still produces the anticipatory freak out. If they still flinch and check their heart rate will be checked before, like literally like 30 seconds before this occurs and before the drug even is given, to check if the drug has impacted heart rate. If the lower doses are known for producing stimulant effects, then this might indicate that the heart rate increase is drug induced, and we'll check immediately before the drug is before the uh, sound is presented, so that we can see if their heart rate before and after the sound and make sure that it's changed at all. Okay, so the next test is the series of illusions so there'll be the Ebbinghaus illusion, the Chubb illusion, the Muller-Lyer illusion, the three flash illusion, the inverted mask illusion, and the motion after effect illusion. So most of these, I suspect, are based in a kind of long-term memory. And the reason I say that is because So with this example, for example, this Ebbinghaus illusion that's on the screen right now, this doesn't seem to be something that you learn in short-term memory, for example, whereas something like the motion after effect is clearly, if it is related to memory, it is clearly an effect of short-term memory because uh, you're presented with a stimuli that repeats over and over until your brain starts predictively assuming that there is still motion even when there isn't. And that is clearly a short-term illusion because it doesn't occur unless you present stimuli to someone in a very short period of time, and the effect decays in a matter of like 30 seconds. Whereas this is something that is probably primed over the course of your life. And that there's evidence of that because uh, there's been studies about cultural differences in some of these illusions. For example, the Muller-Lyer illusion, there's a difference if you live in a rural area versus a city area. People that live in the city areas have really strong responses to this illusion. And those who live in the rural areas don't. And this might be because there's less buildings. And I forgot to include the example of the Muller-Lyer illusion, but it's basically the one that is two lines next to each other that are the same size, but they have these arrows on the ends of them, and one line looks really small and the other line looks really big, but they're actually the same size. And this might be due to the way that there are so many lines in city environments. We're presented with so many lines that we end up habituating our responses to them because we've had enough time and enough exposure that we can predict what we're seeing without actually trying to analyze the environment by directly looking at it. So, for example, those who do not respond to this illusion, I am claiming here that it is partially because they're consciously looking and analyzing what they actually see as opposed to relying on a kind of habituated or conditioned response. They're not relying on their memory of kind of associative habits, visual habits. Instead, they are seeing what's there and they can just observe that the lines are clearly the same. And that is kind of like the same argument I made with the inverted mask illusion is that the reason that schizophrenics might not be prone to seeing the illusional this illusional effect might be because they're actually more consciously seeing this and they're using the data about dimensionality to determine what they're seeing rather than focusing on like an archetype of what they usually see, like faces is like more symbolic, whereas looking at the shadows and dimensionality of it is going to reveal that it is inverted. Okay, I already mentioned that. So the motion after effects, this may test summation and short-term learning. This is interesting because I want to see if there's any difference in the dose dependency on this compared with other illusions, and if this illusion is affected at all, because there's no data, there's no research about this. It seems like there's not very much research on illusions, especially nowadays. I think a lot of people don't focus on perception or just kind of basic research on perception because it seems like some arbitrary, just randomly interesting topic, but it might actually be a useful and simple tool for future research. Okay, so here's an agnosia test I found online. This is supposedly a way to test for agnosia where people with visual agnosia cannot see this as a chair because there's so many gaps, and most of you who are watching probably can tell that that is a chair. This as well is a chair, and that is a different way of testing it. The angle is very strange. Just head over. So I want to test ignasia because of the supposed claims from anecdotes uh, that the higher doses of NMDA receptor antagonists produce ignasia. And I think this is significant. I don't think I mentioned this, but one reason that this is really important is that the loss of illusions experienced in schizophrenic subjects might actually be early stages of visual agnosia. You can imagine that objects themselves are illusions, like this. The fact that we can identify a chair from this may be an illusion on some level. It may not have the same kind of properties as the other illusions that we're presenting, but this is clearly not actually a chair, like in in many of the ways that you can interpret it. Like this is just a bunch of lines. You could argue that this you're looking at a flat screen, and that the idea that you can kind of detect a three-dimensional model from this is nonsensical because there's no three-dimensionality to what you're looking at all. This is an illusion that you have depth perception models, for example. And so visual agnosia might just be a really severe case of the same thing that's occurring with the loss of illusions. And it's also really significant because NMDA receptor antagonists are shown to reduce illusions, and people are claiming that they may also induce agnosia at very high doses. So this could end up revealing the nature of perception, and we can use perception to understand what is happening to other people. For example, if dynorphin activity is linked to depression or schizophrenia or trauma, we can determine if someone's like traumatized and experiencing uh, visual symptoms, or maybe they don't even recognize that they're traumatized. Uh, well, I don't know. We don't need to get that gets into way more complicated territory. Um, Another thing that's really interesting, though, about agnosia and this loss of illusions is that there's actually a lot of okay. So actually, let's start here. There's actually some research showing that visual agnosia can be used as a indicator of Alzheimer's and dementia. And this is really interesting because a lot of the mechanisms between schizophrenia and Alzheimer's are overlapping. They're actually the same. So for example, there's increased beta amyloid in both conditions. There is advanced aging of the brain in schizophrenic patients. I think it was when they're 20 years old, they show an 8-year increase of brain age compared to healthy subjects and compared to bipolar subjects. Both involve impairment on 5-HT2A serotonin receptors. And that's particularly interesting because those receptors are involved in enhancing NMDA receptor activity and long-term potentiation. And there's papers that go into the effects on cognition and memory enhancement. And there's also evidence that agonists of this receptor decrease the depressant effects of kappa opioid receptor agonism. And that's really interesting because both schizophrenia and Alzheimer's patients have increased dynorphin activity, which is the kappa opioid receptor agonist of your brain. And so, oh, and dynorphin has also been studied in aging models and Alzheimer's and all this. When they studied it in animals, the removal of dynorphin genes attenuated age-related cognitive decline in mice, and it also it prevented a lot of different downstream changes to glutamate receptors that might help to explain changes of long-term potentiation, changes at NMDA receptors, and all that. And if we look at beta amyloid, that is really interesting because it stimulates NMDA NMDA receptors, and this is thought to play a role in brain damage in Alzheimer's because of overstimulating that receptor is excitotoxic. It ends up allowing calcium to enter the neuron, which destroys its functionality. So there's a lot of interesting implications here. I think that stimulating the NMDA receptors through beta amyloid might tie into dynorphin release. And there's also studies showing that uh, injecting beta amyloid into mice decreases the 5-HT2A receptor count in the brains of the mice. And so there's probably some kind of biological loop going on here where serotonin keeps decreasing, dynorphin keeps increasing, impairing learning mechanisms, where it's maybe trying to stop beta amyloid from binding to these receptors and frying them, but then it ends up kind of pitting you in this psychotic haze. And dynorphin also can damage the brain as well. So there's probably multiple mechanisms that are damaging the brain and suppressing activity, which leads to just like a looping of these degradation of consciousness or cognition. I mean, not well, maybe both, but I didn't mean to say consciousness. So I think that probably Alzheimer's and schizophrenia research doesn't often get talked about as overlapping because the people who are researching both disorders are probably not the same crowd of people. A lot of people might not get interdisciplinary. So people who get really deep into Alzheimer's might just completely not know about schizophrenia, or what they do know, they will just assume that they must not know enough and that it's just an entirely different problem. And likewise for people who are exclusively in schizophrenic research. And this is kind of an interesting problem because the way we view these conditions so differently might actually change the outcomes of these disorders. I think there's some research linking trauma as a risk factor for Alzheimer's. And obviously, with schizophrenia, that has been like a focus for a long time, trauma, and there is a risk factor for schizophrenia. But then it gets complicated if you start thinking of the way that schizophrenia is pretty stigmatized, and especially before the person is diagnosed, it probably often involves like people just viewing the person as slipping up and being irresponsible, especially because this is thought to occur mostly in the age range of like 20 years old. And that's also when people begin to lose their plasticity and stuff like that. And that might be a factor for why the problem gets much worse at that time. So I haven't talk too much about this, and this just as a warning is entirely hypothetical, but I kind of think that the loss of plasticity in adulthood is not necessarily due to like just I don't think it's like a clock or something. I think that life gets stressful and you are forced to kind of stop investing your time in kind of open, free exploring behaviors. You end up focusing on some kind of job. Your ability to uh, just kind of leisurely explore reality and learn new things reduces greatly as the pressures of life begin to set in. And life gets much harder during college. Uh, and if you go homeless at this time, that's like obviously much worse, and you're not going to have the kind of privileges to explore and keep your mind sharp. So I think that's a factor. And then if someone has Alzheimer's, you could imagine that maybe trauma is a factor, but then also maybe loneliness and a decline in someone's life to where like there's just literally nothing stimulating and they just pace back and forth in their house all day and all of their abilities just kind of degrade away and they eventually become similar to the schizophrenic who is being crushed under stress in their 20s, but under entirely different circumstances, and people will kind of pity the person that's in dementia. Everyone will probably kind of back out and get more disturbed by both people, in fact. But uh, in the case of the person with dementia, I think a lot of people pull out because it's like kind of traumatizing just to be around a person that's seems to be like disappearing in front of your eyes and like um I don't know. I think that would just kind of accelerate their lack of stimulation. It'll worsen their depression. And depression has been associated with Alzheimer's as well, which is another interesting point. So you can imagine that they get depressed first and then do nothing in their daily life. It becomes really repetitive. Their ability to maintain their cognition declines, etc., and so on. Okay, so that's like one of the most interesting implications. We're almost done here. Many of the other receptor types in the brain modulate NMDA receptor activity, like the 5-HT2A receptor was mentioned. There's also the mu opioid receptor does, D2 receptors, D4 receptors. There's a lot of different mechanisms that seem to converge and manipulate kind of what goes on at NMDA receptors or even AMPA receptors. And I think that those might be the core of a lot of different effects that different systems have, that a lot of other systems are producing their effects by modulating glutamate activity at the core. But that's maybe a bit hypothetical there to say that that's like the core of everything, but it might be. And then we kind of mentioned that people who want to study the shape of the kind of shape or organization of neural systems that produce perception could possibly use these compounds to subjectively try to observe what disappears first. Like if we could design a whole series of tests eventually, not just agnosia tests or illusion tests, but a whole series of tests that end up revealing an organization. Like probably people that have agnosia don't have intact illusions. I'm guessing that I would imagine that people that are that far into severe visual system deficits are not going to also still see the inverted face mask illusion, for example. That would probably like maybe for certain illusions that are like probably some of these illusions might be testing different layers, but I still have a suspicion that a lot of cases of agnosia might not they probably don't see illusions, and that's something that this study here even might be able to reveal, depending on how the dose dependent changes happen in each group. But I think we'd still need a lot more further study to specifically get at that problem. The three flash illusion that was mentioned can kind of provide evidence also for coincidence detection that maybe the short-term memory learning problems are because coincidences and associations don't even form. And this is really interesting because those with schizophrenia have impairments to associative learning. And I think that, and also people on NMDA receptor antagonists also have impairment. And I think that, well, I don't know where I was going there. I think this is pretty much it. We are at the end. Let us just end here. Thank you for showing up. 2 of you actually came. That is very cool. And thank you, Professor, for your class. This has been really cool. And I will see you later. This is probably way longer than it's supposed to be. I'm so sorry. Hopefully it's interesting, though. Hopefully I actually covered the bases, too. So thank you, and that's it.